Okay, so welcome back to another video. So in today's video we have the following improper integral containing a infinite product series of a trigonometric function. So we have the integral from over the real line, negative infinity to infinity, of the infinite product series of cosine of x divided by 2 to the power k dx. And there was a similar video I did in the past where, well, it's not really dealing with the trigonometric function, of course, but it was dealing with both a combination of both an integral and a product series. So if you want to check that out, I'll leave that a link in the description below. But since we're dealing with a trigonometric function, so things are going to get a little messy here, I preferably like this because when I was trying to solve this out, we actually had to use specifically the double angle formula to rewrite the trig itself. We wanted to, so I'll say this first as the first step. Technically, we want to evaluate the product series first, but instead of evaluating cosine itself, we want to evaluate sine, manipulate that, and so we get some equality in a way that we can set cosine equal to what the closed form of the, not really a closed form, but some sort of generalization for the cosine function. Then that way that gets us to getting to the part of integrating that, set function of that infinite series. But there's a lot going on there, but it's going to be very interesting. Even especially with once we get to the next second big step when it comes to integrating the product series, well, after finding that. So anyway, I don't have any other remarks because I don't want to spoil much of the work, as you'll see. So let's just jump right in. So I'll call this capital I, so let's see if I just write equals I over here. I don't want to feel like writing the same thing again. So in this case, we would have to write this in a limit, so I'll call this I, or, well, not really I, because I is the whole integral. Specifically, what I want to do is, as I mentioned, that we want to evaluate this infinite product series before we actually take the integral. So let's evaluate this, but actually let's also write this in terms of a limit so that way things can be easier when we're trying to analyze this a little further. So I'll just write the same thing over here. Then I'll set this equal to the limit. So instead I'll write this as n approaches infinity of our partial product series, k is equal 1 of cosine of x divided by 2 to the power k. Now let's actually start. Now, I already said this. We're going to start with sine of, well, the product series of sine, the partial product. So the partial product of sine of x divided by 2 to the power k. So we're going to start there. And of course, we're actually be using the double angle formula. So that says that the sine of 2x, that's equal to 2 times sine of x, then multiplied by cosine of x. So we'll do that from there. Now I'll actually just switch to the purple marker this time. So from here, then I'll just apply the double angle formula to our series that we're actually taking the product expansion of. So when we do this, so this is k is equal to 1. So this is 2 times x, so let's say we deal with this input. So if I had to rewrite this, well, first I had to write 2 times sine, then that new input for applying that formula, so we would get that this is x divided by 2 to the power k plus 1, then multiply with cosine of x divided by 2 to the k plus 1. Okay, so from there, now we can actually expand this series further out. Well, really, it's a product of the series since, again, this is a product series. So we have a 2 over here. So if I expand that series out, so it's 2 times however many you want it to be, all the way up to n times. But since it's the same base, so it's basically treat that as an exponent. So this will become 2 to the power n. Then I can just, it's all product series, so I can just write this as a product of the product series, the partial product, really. So this is the partial product of sine of x divided by 2 to the power k plus 1. Then multiply with the product of cosine of the same input. So x, then 2 to the k plus 1. Let me fix that. That's good from here. So now we're going to actually evaluate these two product series over here. So here we're going to make some notes that we want to simplify the algebra from there. So let's make some notes here. So we want to note, we're going to first evaluate the, evaluate, but in that sense more find like a little generalization. So we note that the partial product of our sine function x divided by 2k plus 1. And then what we can do is we can just fix the index over here. So I'll put this as our upper index as n plus 1 and our lower index starting from 2. Then if we were to write this out, adjusting the index from the inside, then we have that this is just x, then divided by 2 to the k. Then from here, what I can do is I can actually just, write it on this line. Then if we just readjust this back to our original product series, so since we started with the next index going up by 1, so this moves up to plus 1. So what that entails is that if we want to convert this back to our starting product series, that means I would have to expand the term for evaluate the term at n plus 1 and k is equal to 1. So if k was to equal 1, so that means this is sine of x divided by 2 to the k. Since it starts at 2, so that doesn't exist. So if we were to rewrite this, that would have to divide whatever the k equals 1 evaluation at for the sine of x function over here. Do the same thing for n plus 1, but it's since it starts with n and then adjusts to 1, so it's basically just multiplying that n plus 1 term evaluated. So that way we have the, now in this case, we would have sine of x divided by 2k plus 1. Then that would have to divide that with sine of x divided by 2. This way we evaluate it at k is equal to 1. Then this is just multiply out the product of k is equal to 1 of sine of x divided by 2 to the power k. So I'm going to do this. Let's just underline the whatever we have for this. That's to say that this is equal to here. Now we have to do the same thing, but instead this is for cosine, but the same method can apply. We're pretty much just doing the same method here. So now this is the same thing, but except this is now cosine of x divided by 2 to the k plus 1. Readjust that index, so we're going to start with n plus 1 from the top bound, and then k is equal to 2 for our starting index. Then if we just readjust this, this is cosine of x divided by 2 to the power k. Okay, and then just evaluate this out even further. Rearranging it so it looks like in this form, it's basically the same thing, just instead now it's just cosine. So we have cosine of x divided by 2 to the k plus 1, then divide this with cosine of x divided by 2. We'll just write it like that. Probably do the same thing on the one. It's okay. Then multiply with the partial product. K is equal to 1 of cosine of x divided by 2 to the power k. So we have what we need. So now it's just basically just substituting what we just expanded out, the new expansion really, in a more simplified and elegant way. So then we see that now sine of, actually I have to write this back at the product series again. We have the partial product of sine of x divided by 2 to the k, all right? So far we expanded it out to say that this is just, now we just plug in whatever we just expanded out. This is 2 to the power n, then multiply with, so this is just, I'm just gonna combine everything together. So this is sine of x divided by 2 to the k plus 1 multiplied by cosine of the same input. Then we just divide this with these two denominators over here. Sine of x divided by 2 multiply with cosine of x divided by 2. Then just put back a product series over here. And k is equal 1 of cosine of x divided by 2 to the power k. Then sine of, or then should have wrote it as the product series again, times the product, k is equal 1 of sine of x divided by 2 to the power k. Now from there, applying the double angle sum again, just to evaluate this form. So let's move on back to the purple marker again. We have that sine of x, or how about I'll put it like this. We'll start from over here. This is just to denote that the arrow's just coming from this expression over here. Not including the 2 to the power n, just this term right here. Like so. There we go. Okay, coming from here, what I can do to manipulate this, let's just multiply the top and bottom by 2. So 2 times sine, Okay, so give me 1 second. We're just writing the same thing again. So x. So we have this. Then we just apply the double angle formula from over here. So if we were to readjust this, that this is just equal to sine of x divided by 2 to the power k, then just divided by sine of x. All right, so there's that. So now let's actually just plug in everything back from in here and simplify things out even a little more further. So now in this case, now we would have 2 to the power n with equals coming from our from the product series that we're evaluating for sine. So this is 2 to the power n, then sine of x divided by 2 to the power k, then divide this by sine of x. Now multiply with the partial product, k is equal 1 cosine of x divided by 2 to the power k, then multiply product again, and k equals 1 sine of x divided by 2 to the power k. Alright, so what I can do here is we can just divide these product series to both sides, and so we're just left with 1 equals this expansion over here. But what's really nice is because we're trying to solve or figure out what is the partial product, well over here specifically, the partial product of cosine. So this is nice since we have this expansion over here. I could just divide, let's put it this way. Let me, if I do the algebra, so let's see, we could just cross this out and I'll cross this out. This is just left with 1 on this side, for example, and then equals this expansion. Then I just divide the 2 to the power n sine x divided by 2k, and then sine of x. By that both sides, it flips the reciprocal. Therefore, you'll see that the infinite product is just of, not the infinite product, the partial product for cosine of x divided by 2 to the power k is just equal to sine of x, and then divided by 2 to the power n, then sine of x divided by 2 to the power k. All right, so that's what we got. And I'll just underline this so we have what we want to achieve. Okay, so now if I were to take the limit, so that means now replace, this is be back for infinity, the infinite product of cosine of x divided by 2 to the k, then to just set this as a limit form. So the limit as n approaches infinity of sine of x, then divided by 2 to the power n, then sine of x to the power, or sine of x divided by 2 to the power n. So in this case, I have to go back and fix something because I have some exponents set for k, but they're supposed to be n. So I'll come back to you once I make those changes. Okay, so now next we want to evaluate this limit over here, but let's actually take into focus of taking the limit from what's on the denominator, since you don't really need to do much for the numerator. There's no variable for n to plug in for the infinity, so we're just going to look at the denominator here. So now we want to evaluate the limit as n approaches infinity of 2 to the power n, then sine of x divided by 2 to the power n. If you just put it this way, it looks like it's going to get infinite. It gets to infinity, but it's not really, you're not going to do justice with that. So how about instead we'll actually manipulate this a bit. I'll change this and rewrite it so that the exponent is a negative n, but if that was the case, that has to move to the bottom and to the denominator. The same thing for over here if we want to preserve this equality over here. So doing so, we have, so the limit n approaches infinity. So that means this will just be sine of, 2 to the power negative n times x, and then divided by 2 to the power negative n. So evaluate this, you're going to see that we get a indeterminate form of 0 over 0. Then by using L'Hopital's rule, I'll put LH for this. Drop my eraser. Put LH for L'Hopital's rule. That means like I have to take the derivative of both the top and the bottom, but you'll see that if I do so, then you're going to get, so the limit. Then evaluate this, take the derivative, so this is just cosine of 2 to the negative n times x. Then you have to differentiate the inside, so we get that this is actually in a form of product. Well, not really a product rule. This is x is the constant in this case. We're taking the derivative in respect to n. So we have now this is just x, and then take the derivative of 2 to the negative n. So you get that this is just negative ln of 2, then times 2 to the negative n. Then the derivative is the same thing just from here. So this is just negative ln of 2 times 2 to the negative n. You'll see that you'll see that the negative ln of 2 times 2 to the negative power to the negative n, that cancels. Then notice if you plug n for infinity over here, this is just going to be cosine of 0, which that's going to equal 1. So 1 times x, so therefore this is just equal to x. All right, so we have that, and I'll draw this arrow to signify that this is what we have. So it means we do the substitution. Now, in this case, this will be, I'll just have to rewrite the product series again one more time, which is totally fine. N is equal 1, then cosine of x divided by 2 to the power k, then that's just equal to sine of x divided by x. All right, cool. So this is what we have so far. So now we can actually keep going and evaluate even further. What do we do from here? Since we already solved that the infinite product series of cosine of x divided by 2 to the power k is equal to sine of x divided by x, we still have to take the integral of that. So we take the integral, that means we have to take the integral of both sides. So now this will be the, so now we would have the improper integral of sine of x divided by x dx. So let's actually notice something, that sine of x divided by x is an even function. So I'll write it over here. Sine of x divided by x is even. Then that means I could write this as 2 times the integral over the positive reals from 0 to infinity of sine of x divided by x dx. Now we want to next define some generalization. So this will help us evaluate the integral that we just stated below. So that's going to be very handy from there. So let's actually define the following generalization. We'll say that the function f of alpha here, so right here is good. So we'll see that f of alpha is actually equal to the, so we say the integral from 0 to infinity of e to the negative alpha x, then times sine of x, then divided by x dx. So what I can do here is, well, actually, let's also note something too. Since we define I is equal to this integral, and then we set that this infinite product series over here is equal to sine of x dx, notice that this is 2 times whatever we found for the product series over here. You'll see that if we were to plug 0 into here, for example, so for alpha equals 0, then we get that this is just the same thing over here. So this is just this improper integral over here from 0 to infinity of sine of x divided by x dx, that's just equal to f of 0. And we say that that's 2 times f of 0. That actually gives us what the integral we want to define. So I'll say this, note I is equal to 2 times f of 0. So this will come in handy eventually later, so let's just put that out there. So now let's actually, we're going to actually take the differentiate under the integral. So in other words, this is actually known as Feynman's technique. So f prime of alpha, then it's equal to the integral 0 to infinity of del x, del x of our following. So it's e negative alpha x, then sine of x divided by x dx. Now if you take the differentiation from there, you'll see that this is just equal to negative, then the same integral, or the bounds I mean, of now e to the negative alpha x, and then sine of x dx. So what we can do from here is to integrate this, let's actually do some integration by parts. So now we'll let u equals e to the negative alpha x, then du is equal to negative alpha times e to the negative alpha x dx. dv, I'll include the negative sign, so instead this will be negative sine of x dx, then v is equal to, cosine of x. So now from there, let's actually just plug in our substitution from there. For the sake of more room, how about I actually move this piece to here? So let me actually make that edit. Coming back, I just fixed this minor change. So now we just do the integration by parts, just substitute our pieces. So what we see is that so far, if we have f prime of alpha is equal to e to the negative alpha x, then cosine of x. Define this from our bounds from 0 to infinity. Add this, well, since it's supposed to be subtract, but I could actually just factor out the, let me see, v times du. So I'll just factor out the alpha, the negative alpha as well, so that'll become a plus. So it's alpha, then multiplied by the same integral, e to the negative alpha x, then cosine of x dx. All right. Then evaluate this even further. If you were to plug 0 in infinity, let's see, this will be 0. So 0 minus, then 0 here. So that will be a -1. So -1 plus alpha of the integral e negative alpha x, then cosine of x dx. So now let's actually, yet again, perform another u sub. So in this case, we have that u is equal to, it's just the same pieces again. Then du negative e, negative alpha e times to the power negative alpha dx. dv equals cosine of x dx. Then v is just equal to sine of x. Next, let's just plug in our pieces again. -1, then plus alpha. That's dealing with this integral, so we have to do this again. So this is u times v. So e negative alpha x sine of x from infinity to 0. Then subtract, factor out the negative again, and the alpha as well. So plus alpha, then 0, infinity, e negative alpha x, then sine of x dx. What you'll notice is that if I plug 0 for here, because we have a sine of x, so sine of 0 is just 0 and then infinity, so 0 over here, so this whole term just vanishes. So I can just distribute the alpha over here, so now this time we have -1 plus alpha square of 0, infinity of e negative alpha x, then sine of x dx, which is what that the same thing we have. We said that f prime of alpha is equal to the Feynman trick, using the Feynman trick from here, right? In further conclusion, we can see that this is just f prime of alpha equals -1, then subtract alpha square. Okay. Right. Because this is a negative, so just substitute that. So that'll change that to negative over here. So negative alpha square. Then, or I don't know how to write the integral again. We just substitute that for f prime alpha. F prime alpha. All right. So now solve further. So I can just add an alpha square to alpha square f prime alpha to both sides. Factor out the f prime alpha. So this will just be 1. Then plus alpha square, then equal to -1, and you'll see that f prime of alpha is equal to -1 divided by 1 plus alpha square. Then here I can just integrate both sides in respect to alpha, which is very simple to do. This is a indefinite integral. F prime alpha in respect to d alpha equals the integral -1 plus alpha square d alpha. Then this is just, we get back f of alpha. Then this is an antiderivative, it's just negative arctangent of alpha. Then add your unknown constant c, which is what we want to solve. But notice that if I take the limit, so one thing you should note that if I take the limit of our function, I guess I can put this over here. The limit as alpha approaches infinity of f of alpha. So go back to our alpha over here, our function of alpha. If I put negative infinity over here, then the whole integral on that right side is actually just going to approach 0. So this is just equals 0. Then if I say the limit as alpha approaches infinity f of alpha, then you have to take the limit again to that right hand side as well. So alpha approaches infinity, negative arctan of alpha plus c, then you see that this is just 0. Alpha approaches infinity, so arctangent of infinity is actually just equal to negative pi divided by 2. Well, arctangent of infinity is pi over 2, but I just multiplied the negative, so plus c. Then you'll see that c is equal to just pi over 2. We have that f of alpha is just equal to negative arctangent of alpha, and then add this with pi over 2. So now the last thing to note is that that's why I wrote that I is equal to 2 times f of 0, because if we plug 0, we're just going to get the integral that we want to show. So I plug 0 for alpha over here. Arctangent of alpha, or arctangent of 0 is just 0. So pretty much f of 0 is just equal to pi over 2. So we have that 2 times pi over 2. Then therefore the final answer we get that is just pi, like so. Oh, that's a doozy right there. And there we have it. Final answer in the blue box. It's actually a simple answer when you think about it, but there's a lot of work that you'll notice that we just expanded out. A lot of crazy things. Yeah, that's pretty cool if you ask me.